Now let's talk about Lagrange multipliers for functions of three variables. So to minimize or maximize a function f of x, y, z subject to the constraint g of x, y, z equals k, we solve the two equations. Gradient of f equals lambda times the gradient of g, where lambda is some scalar and we don't know what it is, and g equals k. Okay, so if you expand this in components, it's actually four equations for four variables, x, y, z, and lambda. And x, y, and z are the ones that we mainly care about. We'll talk a little bit later about what lambda actually means. And a little caveat is you also have to check where a gradient of g is 0. So in other words, if x, y, z minimizes or maximizes f of x, y, z with the constraint g of x, y, z equals k, then we must have the gradient of f equals lambda times the gradient of g for some scalar lambda. And it's the same argument as in the two-dimensional case, but let me just show you again because it's such a nice little argument. Okay, so here's the level surface where g equals k. And also, sorry, I forgot to say, this is an and if the gradient of g at x, y, z is not equal to 0. Okay, right. So here's our point x, y, z, which minimizes or maximizes f. It's on the level set g equals k, and because the gradient of g is not equal to 0 here, the level set near this point is a nice smooth surface. Okay, and then let gamma, or maybe let's call it r, let r of t be a parameterized curve on the level set g equals k with r of 0 equals x, y, z. That's it. Okay. Now then we have that 0 equals d dt of f of r of t, and this is because we're minimizing or maximizing f on the surface. So if this derivative were not 0, then we could move along this curve, staying on the level set to increase or decrease f. And then by the chain rule, this is the gradient of f at x, y, z dot r prime of t. And this is because x, y, z minimizes or maximizes f. And we also have that 0 equals d dt of g of r of t, and that's because g of r of t is a constant. It's always equal to k for all t. And this, by the chain rule, is the gradient of g at x, y, z. And the vectors r prime of t that can arise this way, those comprise the tangent plane to the surface. So the tangent plane is those vectors that are perpendicular to the gradient of g. And those vectors are also perpendicular to the gradient of f. So since every vector that's perpendicular to the gradient of g is also perpendicular to the gradient of f, it follows that the gradient of f is a scalar multiple of the gradient of g. So the gradient of G is like this. The tangent plane to the surface is a plane we could draw like this. Gradient of G is perpendicular to it, and gradient of F is also perpendicular to it, so it has to point, it has to be in the same direction, in a scalar multiple, point in the same direction or the opposite direction. Gradient of F could also be 0, by the way. Lambda could be 0. Okay, so let's do an example of one of these problems. So example, so let's maximize f equals x, y, z with the constraint g equals 2x plus y plus z equals 1. So this should look familiar. This is an example we did before where we were trying to maximize the volume of a rectangular box which fits in a funny shaped tetrahedral room. Okay, now here's how we do this with Lagrange multipliers. Let me also specify that we're requiring that x, y, and z are greater than 0. Okay, so we need to solve the two equations. Gradient of f equals lambda times the gradient of g, and g equals k. So let's work out what these equations mean. So the gradient of f is the vector, well, partial with respect to x is yz, partial with respect to y is xz, partial with respect to z is xy. And the gradient of g is 2, 1, 1. So the Lagrange multiplier equation, gradient of f equals lambda gradient of g. When we expand this in components, it gives us the three equations y times z equals 2, x times z, 2 lambda, x times z equals lambda, and x times y equals lambda. So we have three equations here. Now, these last two equations, these tell us that y has to equal z. Either that or x equals 0 and lambda equals 0. But we're requiring x to be non-zero. So since x is not 0, it follows that z and y have to be equal. In other words, I could subtract one equation from the other and write this as x times z minus y equals 0. And since x is not equal to 0, it follows that z equals y. So here I have z equals y. And okay, so now if I look at these first two equations, and I put in the fact that z equals y, well, now I also know that z is not equal to 0, so I can divide the one equation by the other. Actually, I haven't put in z equals y yet. I can just divide the one equation by the other here to see that y equals 2 times x. Okay, so these two equations give me z equals y, and these two equations give me y equals 2x. So z equals y equals 2x. So this is everything that I get from the Lagrange multiplier equation. But I'm not done. I haven't yet used the constraint equation, which is g equals k. So now we put in the constraint equation, g equals 1, tells us that 2x plus y plus z equals 1, and substituting in for y and z, I get that 2x plus, and y is also 2x, and z is also 2x, plus 2x equals 1. So x equals 1/6. And now using these equations from before, I get y and z are twice that. The y is a third, and z is a third. So this is the same solution we got before, and the maximal value of f is 1 over 54. But this method is sort of more elegant, and so it already looks better in this example, and we'll see some harder examples where Lagrange multipliers are even more valuable.